Welcome to the Deep Dive. You're here because you want to get smart, fast on fascinating topics. Today, we're tackling something pretty fundamental in robotics. It's all about how robots, well, how they see the world.
Exactly. And it's a bigger challenge than you might think.
Right now, robots often have this tricky trade-off, don't they? They might get amazing detail up close.
But then totally miss the bigger picture further away. Or they see far off, but the nearby stuff is blurry.
And that really limits what they can do, how they navigate, how they make decisions.
Absolutely. Imagine driving if you could only see clearly 10 feet ahead, or only see things a mile away. It just wouldn't work well.
Plus, a lot of current systems are kind of specialized, like built for indoors or only looking for one specific thing.
That's a big part of it. They struggle in open, dynamic environments, the real world, basically.
Which brings us to today's deep dive. We've got this research paper, RayFronts, Open Set Semantic Ray Frontiers for Online Scene Understanding and Exploration.
Sounds like a mouthful, I know.
Yeah. But the core idea, we think, is actually quite elegant. Could be a real game changer.
Definitely.
So our mission today: unpack RayFronts. Figure out how it manages to give robots this, unified view, near and far, detailed and efficient.
Sounds good. Let's get into it.
Okay, so what's the central innovation? What makes RayFronts different?
The big idea is integration. RayFronts cleverly combines two main ways of representing the world around the robot.
Two ways?
Yeah. First, for everything that's, within the robot's sensor depth range, the stuff it can directly measure distance to. It uses something called semantic voxels.
Semantic voxels. Okay, break that down.
Think of voxels as 3D pixels, like tiny building blocks making up a map. But semantic means these blocks don't just know where they are in space.
They also know what they are.
Exactly. They store information, semantic features about what kind of object they're part of. Is this block part of a wall?
Right.
A tree? A car? That kind of thing. It builds a really detailed 3D map of the immediate surroundings.
Got it. So that's the super detailed close-up vision, like knowing every blade of grass right under your feet. But what about the hills in the distance? How does it handle stuff beyond that sensor range?
That's the second piece, and it's pretty neat. It uses Semantic Ray Frontiers.
Ray Frontiers. Okay.
Imagine the robot has mapped out an area. The frontier is the edge of that known map.
Right, the boundary between known and unknown.
Precisely. From that boundary, RayFronts sends out these conceptual rays into the unknown space.
Like feelers.
Kind of like feelers, yeah. But these rays aren't just detecting if something is out there. They carry semantic information, clues about what might be out there in that direction, even if it's too far away to map with voxels yet.
Interesting. So the voxels map the known territory in detail, and these rays probe beyond the frontier, giving hints about what lies further out.
That's the core concept. It combines that focused, detailed near vision with a broader, maybe less precise, but still informative awareness of the distant surroundings.
Okay, let's dig into those rays a bit more. How do these semantic ray frontiers practically help the robot see beyond the horizon, as you put it?
Well, the clever part is how they store and use that semantic information on the rays. Older methods had limitations.
What kind of limitations?
Some earlier semantic frontier ideas were often 2D, mostly for indoor spaces, and they might only associate one possible object type with a whole section of the frontier.
So if there was a building and a tree in the distance in the same general direction.
Exactly. You'd get what the paper calls feature collisions. The system would sort of mush the information together, thinking it's maybe one weird building tree object. It loses crucial, distinct information.
I see. That's not very helpful for finding specific things.
Not at all. RayFronts tackles this by sending out multiple rays from the frontier, organized into different angle bands. So one ray might pick up semantic clues suggesting building, while another ray going in a slightly different direction picks up tree.
Okay, so it keeps the information separate using these different angular rays.
Right. It drastically reduces those feature collisions.
Yeah.
This means the robot gets a much clearer, though still probabilistic, idea of multiple different things that might be far away in various directions.
And the payoff for the robot?
The payoff is huge for tasks like exploration or search. If the robot is looking for, say, a specific water tower, like in their example, instead of having to physically go and search this vast unknown area, RayFronts uses those semantic rays to say, hey, there's a high probability of something tower-like over in that direction. It dramatically cuts down the search space. The robot knows where to look first.
That makes a lot of sense. It's like getting a targeted hint instead of searching blindly. Okay, so the rays handle the distance. Let's circle back to the close-up view, the semantic voxels. How exactly do they build that detailed map?
So as the robot moves around, its sensors, like cameras, maybe LiDAR, are constantly gathering data about the nearby environment.
Right.
RayFronts takes this incoming data and uses it to populate that 3D voxel grid. When a sensor reading indicates a point in space is occupied.
It fills in a voxel there.
Yes, and crucially, it associates the semantic features extracted from the sensor data, like the camera image, with that voxel. Over time, as the robot sees the same area from different angles, it fuses this information.
Fuses it.
Yeah, it combines the features, averages them, refines them, so the understanding of what object each voxel belongs to gets more and more accurate and robust as more data comes in. They use an efficient method for this feature aggregation.
Okay, so we've got the distant rays and the detailed local voxels. But how does the system get those semantic features in the first place? How does it know this looks like a building or that pattern is road cracks? What's doing the actual seeing and interpreting?
Good question. That relies heavily on the eyes of the system, which is basically a powerful image encoder. It needs to look at the raw camera images and pull out meaningful semantic information.
And RayFronts uses something special here.
It does. They use a modified version of an encoder called radio. But they've enhanced it by integrating something called NAC Lipic, which adds a spatial attention mechanism.
Spatial attention? Sounds fancy. What does that do in plain English?
Think of it like giving the robot's vision the ability to really focus. When it looks at an image, the spatial attention helps it zero in on the most informative parts of the image for understanding what's where. It helps pinpoint the location of specific features much more accurately.
So it improves the localization of the semantic meaning within the image.
Exactly. And this specific combination, the modified radio with NAC-LP, turns out to be very efficient.
How efficient?
The paper highlights some pretty impressive numbers. They claim it's about 16.5 times faster than a comparable method called Trident.
Wow, 16 times faster.
Yeah, and importantly, it's not just faster, it's also better at a task they call zero-shot 3D semantic segmentation.
Okay, another technical term, zero-shot 3D semantic segmentation. Let's break that down.
Right, semantic segmentation is basically labeling every point or voxel in the 3D map with what it is, road, building, tree, etc.
Okay.
Zero-shot means the system can recognize and label objects or categories it wasn't explicitly trained on beforehand.
So it sees something new, maybe a specific type of bench it's never seen?
And it can still say, that's probably a bench, based on its general understanding of benches from the language-aligned features it learned during training. It can generalize.
That's incredibly useful for real-world robots. They're always encountering new things.
Absolutely. And RayFronts apparently achieves about 1.3 times better performance, higher MIOU, which is a measure of segmentation accuracy on this zero-shot task compared to that Trident system. Their Figure 5 shows this trade-off, mapping throughput versus accuracy.
So faster and smarter at recognizing things, even novel ones. That combination seems really powerful.
It really is.
Okay, so we have this system that seems great on paper, unified near-far vision, efficient semantic understanding. But the real test is, well, the real world, or at least realistic simulations. How do they actually evaluate RayFronts? How do we know it works?
They did quite a bit of evaluation. And interestingly, they realized that standard metrics didn't fully capture the benefit for online mapping and exploration, where the robot is building the map as it goes and needs to decide where to explore next.
Right, because knowing where to look is key.
Exactly. So they introduced a new metric, Search Cut Volume Recall, or SCVR.
A CVR, what's that measuring?
It's designed to measure how effectively the mapping system reduces the search volume. Basically, if the robot is looking for a specific object type, how well does the map, including those frontier rays, correctly tell the robot, you don't need to look over here, but you should look over there? It quantifies the useful reduction of the search space. Figure 3 in the paper illustrates this concept.
That sounds like a really practical metric. Did RayFronts do well on it?
It did. They tested it on a dataset called Tartan Air V2. This one's interesting because it simulates outdoor environments, but often with limited sensor depth, mimicking real-world sensor limitations.
So perfect for testing that near-far capability?
Precisely. And the results, which are in Table I and Figure 4, showed RayFronts significantly outperforming other approaches methods just using semantic poses or just voxels or older semantic frontier techniques.
So performing across the board.
Pretty much. Especially when the simulated sensor depth was limited, like only 10 or 20 meters. RayFronts achieved much higher SCVR scores. It was way better at guiding the search.
Is there a specific example that stood out?
Yeah, they have this great example in figures 4 and 8.2 comparing a search for a chimney versus a building. The chimney's obviously smaller, less prominent, harder to spot from afar.
Right.
RayFronts, using its Semantic Ray Frontiers, was still able to detect the likely presence and direction of the distant chimney and drastically reduce the search volume for it. Other methods really struggled with that subtle distant object.
That really drives home the benefit of those semantic rays for distant, maybe less obvious targets. That's the aha moment right there.
I would guess so, yeah.
Did they only test this SCVR metric, or did they do more traditional evaluations too?
Oh, they did the traditional stuff as well. They evaluated its performance on standard offline 3D semantic segmentation benchmarks.
Using what data sets?
They used common indoor data sets, Replica and ScanNet, and also the outdoor Tartan Air V2 again. And across the board, RayFronts achieved state-of-the-art results in terms of MIU, that accuracy measure for labeling the 3D environment. Tables 2 and 3 and figures in the appendix show these results.
So it's accurate at labeling the detailed maps, too, not just good at the search guidance.
Correct. And they noted it handles background class as well, which is sometimes tricky.
Okay, simulations and benchmark data sets are one thing. What about, an actual robot? Did they try it in the real world?
They did. That's often the ultimate test, isn't it?
For sure.
They put RayFronts onto a robot with a pretty powerful onboard computer, an NVIDIA or an AGX, and tested it in a real outdoor location. Looked like some kind of fire training facility from the pictures.
And how did it do? Did it run in real time?
Yeah, they reported it running at about 8.8 frames per second, which is definitely real-time performance for this kind of complex scene understanding task.
That's impressive. And could it handle the complexity?
It seemed to. Figure 1, the main figure, actually comes from this real-world test. It shows the system simultaneously reconstructing fine details right near the robot, like cracks in the road, while also successfully detecting and mapping that distant water tower using the Semantic Ray Frontiers. It really showcases that unified perception in action.
Wow. Seeing it work on a real robot, handling both the tiny details and the big distant objects at nearly 9 hertz, that's pretty convincing.
It certainly suggests the approach is practical, not just theoretical.
So, thinking about all this, for our listeners trying to get smart on this, why does RayFronts really matter? What's the bigger picture takeaway?
Well, if you zoom out, advancements like RayFronts are crucial steps towards making robots much more capable and autonomous in complex, unstructured real-world environments.
How so? Where could this be applied?
Think about autonomous navigation, obviously. Cars, drones, ground robots moving through cities or wilderness. But also things like search and rescue.
Oh, right. A robot entering a collapsed building.
Exactly. It needs to map the debris nearby, identify hazards, and potentially spot signs of a survivor further down a damaged corridor. This unified perception is vital. Or environmental monitoring drones, identifying specific types of vegetation or geological features over large areas. Construction, agriculture. Anywhere, a robot needs a comprehensive understanding of a large, dynamic space.
So the aha moment is that this isn't just an incremental improvement. It's potentially enabling robots to operate in ways they couldn't before.
I think that's fair to say. It addresses a fundamental limitation, that near-far trade-off, the lack of semantic understanding beyond sensors. RayFronts offers a way to get a more complete, more semantic, and surprisingly efficient picture of the world. It's moving beyond those narrow, restricted views.
That makes the potential impact really clear. Now, before we wrap up, were there any caveats, any downsides or limitations mentioned?
Yeah, it's always important to look at the trade-offs. The researchers are upfront that RayFronts generally requires more memory than some of the simpler baseline methods they compared against.
Okay, so there's a memory cost.
There is. However, they also point out that the system is tunable. You can adjust things like how many angle bins the rays use or the depth range you consider near. So you can potentially trade off some performance or detail to reduce memory consumption depending on the robot's hardware and the specific task.
So it has some flexibility there. Good to know.
Definitely.
Okay, so to kind of summarize our deep dive today, RayFronts looks like a really significant step forward for robot perception. It elegantly integrates this detailed, close-up semantic mapping with a long-range semantic awareness using those clever Ray Frontiers.
And it does this with impressive efficiency, thanks to that fast attention-guided image encoder.
Yeah.
It seems to genuinely bridge the gap between seeing the details and understanding the broader scene.
It really feels like it gives robots a more complete, more human-like in some ways understanding of their surroundings.
That's a good way to put it. More holistic.
Right. Which leads us to our final thought for you, the listener. As systems like RayFronts mature and robots gain this much richer, real-time understanding of the messy, complex world, how does that change things?
Yeah, how will that fundamentally reshape what robots can do in our homes, in industry, in exploration, in dealing with emergencies?
What new possibilities open up when machines can perceive and comprehend their environment with this level of detail and scope? Something to definitely think about.